All right. Two identical masses with masses of 1 kilogram each are at the ends of a massless spring which is held by a string to remain at a length of 50 centimeters. The system spins at 2 revolutions per second about an axis through its midpoint. Suddenly, the string is cut, allowing the spring to relax, and the masses expand outward to a maximum length of 160 centimeters. So first of all, what is the rotational frequency in revolutions per second of the masses when they're maximally separated? So this concept, whenever you are seeing things that are rotating, you might want to ask yourself if angular momentum is relevant. The concepts here are angular momentum, and in particular, conservation of angular momentum. So let me write it this way: conservation of angular momentum. You may ask, how do you know whether you can apply conservation of angular momentum? The condition to use that is that the net torque on the system has to be equal to 0. The net torque is what ultimately changes angular momentum. So if there is no net torque, then the angular momentum doesn't change. So it's the same before and after. How you would write that in terms of equations: in vectors, the initial angular momentum is equal to the final angular momentum. And now, since we're going to deal with an object that's spinning around in a particular plane, we can just work in the plane and deal with rotation that's clockwise or counterclockwise. In fact, we'll assume everything is going counterclockwise, as shown in the picture. So we can write that in just the plane like this. Okay, so we have our equation that describes conservation of angular momentum. We also have a definition for angular momentum. Can be written for a point particle, but also for a semi-rigid object, which we can deal with here. It's the moment of inertia of that object times its angular speed, omega. Now, the moment of inertia, how do you compute that? Remember that the moment of inertia for a point particle is given by the mass times the distance squared, and this is for point particle, where mass is obvious, but r is the distance from the axis to where the mass is. So in this problem, we're going to be measuring r from the center of the rotation, that'll be the axis, to where the mass is. Let's call this r naught, and the other mass is at the same distance. We can call that r naught. Okay. Afterwards, after it is expanded, the distance that we'll have is r final, and this will be r final. Notice that those distances are half of the length of the separation. Okay. So let's go ahead and apply conservation of angular momentum, setting the initial angular momentum, I initial times omega initial is equal to I final times omega final. Not only does the angular speed change, the moment of inertia changes. In fact, they must change in ways that make sure that this equality holds. We're interested to know what is the final angular frequency, rotational frequency. In other words, we want this. So let's rearrange this equation and write it this way. The initial moment of inertia divided by the final moment of inertia times the initial rotation frequency is equal to the final rotation frequency. We can start to plug in numbers, but let's perhaps wait just a moment. The initial angular frequency, or angular moment of inertia, is given by, there are two objects, each of them has a mass of m, and they sit at a distance of r naught squared away from the axis, so I can write it this way, but realize that's just 2m r naught squared. The final moment of inertia has a similar form, but it's at a distance of r final away. And so, when I go to apply the relation that we just found, the initial moment of inertia, 2m r naught squared, divided by the final moment of inertia, 2m r final squared, omega naught, equal to omega final. Notice what happens is that the 2 cancels, and so does the m. In fact, the mass of these objects is irrelevant for determining the final rotational speed. So we're ready to take this further. The value for r naught and rf can be determined. Think about the initial length, the initial separation is 50 centimeters. R naught should be half of that, which is 25 centimeters, which is the same as 0.25 meters. R final should be half of the length, 160, so 160 centimeters divided by 2, that's 80 centimeters, which is the same as 0.80 meters. Now we can plug in what we have. 0.25 meters over 0.80 meters. Each of those is squared, so maybe the way to write that is like this. The initial rotational frequency is 2.0 revolutions per second. Since we want the answer in revolutions per second, there's no need to convert to radians. And when we work this out, we find that this comes out to be 0.01953 revolutions per second, which will round to 0.020 revolutions per second. Now in part B, we want to know by what amount does the kinetic energy of the system change. So if it does change, we can determine the change in kinetic energy by taking the difference of the final minus the initial. Keeping in mind, the equation for kinetic energy of a rotating object is given by 1/2 its moment of inertia times its angular speed squared. In this case, therefore, we have to take the difference of 1/2 the final moment of inertia, final angular speed squared, minus 1/2 the initial moment of inertia, initial angular speed squared. So we can work this out as long as we have a list of everything we need. Let's go ahead and make that list. The final moment of inertia, 2mr final squared. We've already determined that the final value of r was 0.80 meters. So here we find the final moment of inertia is given by 1.28 kilogram meters squared. A similar formula for the initial moment of inertia, 2m r naught squared. That gives us 0.125 kilogram meters squared. The final angular speed is something that we determined to be 0.01953. Notice I want to use all of those digits before I do my final rounding. Revolutions per second. At this point, I need to convert my angular speed into radians per second if I'm going to compute anything else with that. There are 2 pi radians for every 1 revolution, and so you should determine that the angular speed here, 0.1227 radians per second. And finally, omega naught was 0.020 revolutions per second. The same conversion will take place, and we find that this was 1.257 radians per second. All of those numbers can now be plugged into this formula. You'll discover that it's minus 0.0891 joules, which you can round to minus 0.089 joules. The energy, the kinetic energy, I should say, actually does go down. And you may wonder, how is that possible? Does conservation of energy hold? I would say yes, it does. If the kinetic energy went down, what must have gone up? I'll leave that to you to think about.